Hello, in this video we're going to look at the mean and the variance of a Poisson distribution. More specifically, we're going to derive the mean and the variance. So X is a Poisson distribution with the PDF of this. F of X is equal to e to the minus lambda to the X over X factorial. Lambda is positive, our domain is positive or non-negative integers. First, let's show that it is a PDF. So we need to sum it over all the possible values. And then when we plug in the distribution function, this doesn't have an index, so it can come out front. And this right here is a Taylor expansion of e to the lambda. So put that there. Combine those, we get an exponent of 0. Anything to 0 is 1. So it is a PDF. The mean of X, we sum over all possible values and we plug in the X and then times the probability of obtaining that X, which is this. Here, notice that when X is 0, that's 0, so this is 0. So we might as well start summing at 1. And that's what we do in the next one. But the X, this X can cancel with one of the X factorials, reducing it to X minus 1 factorial. And then these will stay the same. There's no index on this, so it can come out front. That's this. We can break this lambda into lambda times lambda to the X minus 1. So their product is again lambda to the X. And then we take out one of those lambdas, and then we're left with this. Well, this is an index, so it can be anything it wants to be, or we can have anything it wants to be. So let's start it at 1 less. So like when X is 1, this is 0, and that's 0. So let's just start it at 0 and get rid of the minus. So you could probably say let Y equal X minus 1 and then substitute in and it would be fine, but we'll just keep it X. And then so this is this, and again that's the Taylor expansion. So that ends up being 1 and we just get lambda. So the mean of a Poisson is lambda. Now before we jump into the variance, we're going to look at what's called the second factorial moment. And it's basically because there's two terms here, 1, 2, and it's sort of factorial like. So it's a second factorial moment. So now it says put this in, sum over all possible values, put this in, and then the PDF in also. Now notice that when X is 0, this is 0, and when X is 1, this is 0, so we might as well start summing at 2. But then this can cancel with the first two terms of X factorial. So those go in there and become this. The e to the lambda stays the same. The lambda to the X, we break it up into the lambda to the X minus 2, lambda to the squared. So when you multiply those back, you get lambda to the X. Well, there's not an index, there's no X index here, so we bring it out and we bring this one out. But we also do an index change, so you let like Y equal X minus 2, and then this just becomes Y factorial over Y, and this Y is going from 0 to infinity. But we just, instead of calling it Y, I just call it X again. So this is equivalent to this. Well, this is the Taylor expansion of e to the lambda. And then when you combine those, it's 1 and you get lambda squared. So to look at the variance of X is expected value of X squared minus expected value of X quantity squared. But to this, let's subtract and add the same thing. So we're adding 0 to this equation, but this right here is what we calculated here. So that's X squared minus X, which is what this is. So this piece becomes lambda squared, That's lambda we just calculated minus lambda squared. So this becomes this, and then those cancel and we just get lambda. So the variance of a Poisson is lambda. And one note about factorial moments for a Poisson, the nth factorial moment, meaning there's n terms here, is just lambda to the n. We're not going to prove that, but you can kind of use the same approach here and show that it's true. So that's all I have for today. Hope you enjoyed the video. If you did, please like it and subscribe so you don't miss the next one. Thanks. Bye.